Okay, this is a lesson on actually creating lists of outcomes so you can calculate probabilities. What we're talking about is here is if someone says, what's the probability of a random day being a Monday? It's quite simple for us to know, oh, Monday is 1 out of 7. What's the 7 come from? Well, 7 comes from there being Monday, Tuesday, Wednesday, Thursday, Friday, Saturday and Sunday. And the 1 comes from there being one that I'm interested in, which was the Monday. What's the probability a day begins with Tuesday, the T? So again, list the outcomes. We've got 7 outcomes. And how many of them begin with T? 2. Tuesday and Thursday. So that would be a probability of 2 out of 7. Similarly, probability beginning with an S. With an S is going to be again 2 Saturday and Sunday, so it's 2 from the 7. Probability a day begins with a P. Well, none of them begin with a P, so 0 out of 7 or just 0. And these are the sorts of questions you get asked. Sometimes you might get things like, what's the probability? It comes after I in the list. Probability of the day. That'll leave that one for a moment now. I'll go with that as an example. Just remember, all of these things, the probability is 1. So if I said, what's the probability of it not being a Monday? That's 1 minus the probability of being a Monday. So probability of not Monday can be written in 2 ways mathematically. One is the probability of Monday, but with a not after it. This little mark afterwards means not. So if you see that after something, it's the opposite. Okay. Probability of not being a Monday, well, that is everything, the 1, minus the probability of a Monday. So we have 1 minus 1 over 7, put them into our common fraction. Common denominator is 7. I had to multiply that by 7 to get here, so 7 minus 1, 6/7. Yes, you can jot those through quite quickly, but often knowing the not is quite useful. More from engineers' side, they prefer to say things like mun with a line over it. Mathematicians avoid this because this has special meaning. This something with a line over it is what is the mean. But engineers, computer scientists, they may use this line over, which, whilst is not wrong, it's just slightly different to what mathematicians are used to. So we've got to be able to produce these lists. So I'm going to give you a situation. I'm going to give you the cards. Let's go for X and Y to start with. And my question is, each card is unique. They are not repeated ones. So my question is, what's the probability that if I randomly draw the cards, I get X, Y? They're not allowed to mix up. There is only one of each card. So think about how many combinations are there of X and Y. Well, there's X, Y, Y, X. Which one am I interested in? I'm interested in the X, Y. So that gives me probability of 1 over 2. There are 2 possible outcomes, and I'm only interested in, or I am interested in, the XY outcome. We can extend it a bit further and go to what's the probability of 4 letters. Let's say they are K, L, M, N. I've got 4 letters. Let's go for 3. It's a little unfair to do 4. I'll do a special video as an extension to this on there being more than that, because there's a special way you can calculate how many things are. But 3 items, you can do it by exhaustion, trying how many lists are there. So if I'm looking for probability that there are, it comes out as LMN, LMK. I need to know how many ways are there of arranging KLM. Now, you can do it just by trial and error and crossing things off. It's often quite useful to do a pattern. The easiest pattern that I know for doing this is keep taking the last item and move it across 1. And you move it until it's been to every place. So M moves across to K, M, L. That's not one I've seen before. If I move the M again across 1 place, I've got M, K, L. I can move, I've now been, M has been in all 3 places. It doesn't mean I've had all trials. There's another combination I can do, but they will come out when I try the next step. And the next step is start again with the last letter. And I go L, and I go L, M, L, K. Move it again, L, M, K. And the last thing I've got is just 1 place, which is take this last K, move it 1 place over. I've now got L, K, M. And if I try moving it once more, what I've actually come to is K, L, M, which is the top item again. So I've actually done only 6 different methods. 1, 2, 3, 4, 5, 6. I was asked for the combination of LMK, which is LMK, that one, the one numbered 5. Numbered 5, not there are 5 of them. So there's 1 method out of 6. One last example, and it's, I have 3 children. Let's go for this being in yellow. 3 children. None of them are twins. And the question is, what's the probability of me having the 2 oldest children being boys? 3 children, boys or girls, no twins. So we need to decide a way to write and include this. So we think about each children. The first position we're going to say is the oldest. The middle one is the middle child, and on the right I have the youngest. Now, it's not quite the same as the previous list. The previous list was 3 separate things. Now I've actually got less than that, less options. But I could start off with the oldest being, all 3 being boys. Think about changing them around. 1 girl. So let's list all possibilities with the 1 girl. We'll start off with the youngest girl. What's the possibility of the middle being a girl? Probability, actually, if I rearrange this, there's a nice, actually, I'll just put a line through. So that's all boys. List all possibilities with all boys. Now we're going to list all 1 girl. So 1 girl, there's the girl in the middle, boy on the end, and girl is oldest, boy, boy. Now, some of you might realise that the next step, 2 girls, is actually a similar pattern to what we had with 1 girl, but where boys and girls are swapped. This is actually a situation which is the same as doing 1 boy. So what I could do is I could swap boys and girls from this section and switch them over. An alternative would be to start with boy and 2 girls. So move that girl over, that one moves to there, that's the same. So we can now only move one girl to being oldest, and the boy and the girl. Keep scrolling on. Effectively, the boy is moving this way now. We've got 2 oldest girls and 1 youngest boy. And you might see by the pattern, what I actually have is, well, at the end, the last option is all girls. Sorry about this. In the evenings, at the end of the day, my tablet gets a bit jumpy. It seems to miss out some of the codes. So we do girl, girl, girl. So list all the possibilities. And the question was, what's the probability of having 2 old boys? It doesn't care what they are. They just, in which cases are there, how many cases are there where the boys are oldest? Well, the first question is, how many outcomes are there? 8 outcomes. How many of them have 2 older boys? Yes for the top line, yes for the second line, no for the third, no for the fourth, and then no for any of the others, because these have now got 2 girls. So we have 2 out of 8, or a quarter of the occurrences could be 2 girls. Similar question could be, what's the probability of oldest and youngest being the same? Oldest and youngest, so that should be a Y. Still got the same 8 outcomes. Oldest and youngest being the same, so yes, the top line. No for the second line. Yes for the third line. Fourth line, no, because we've got a girl boy. I'm only looking at these 2 outermost ones. No for the next one. Yes for 2 girls. Girl boy, no. And yes for 2 girls on the outside again. We've got 1, 2, 3, 4. Yeah, in half the cases are boys and girls. The oldest and the youngest, are they the same gender? Okay, so this is how you can use multiple listings to help diagnose a problem. Let's save that.